All right, so we progressed through chapter 2. Should have a reasonably good understanding of molecules and compounds, names associated, that sort of thing. The next step we want to take is to use that information we have about molecules and compounds and start to look at chemical reactions. So when we combine different molecules, what can happen in that reaction? The other thing that we'll look at in this chapter, in addition to how this relates to chemical equations or reactions, is looking into some of the deeper calculations we can do within a molecular formula, right, or the formula of a compound. But to start off, we want to think about writing out a chemical equation, and the key thing is that equations need to be balanced. So to balance equations, what we really need to do is have the same number of different elements on each side. So same number of atoms, and I'm going to put elements there as well because it can't just be the number of atoms, it's got to be the same type of atom. Same number of atoms on each side of the reaction. Now, there are two sides to a reaction. If we look down here at the first reaction, I can kind of show you that. The arrow is kind of the division in the middle that separates the reactants side. So on the left is where the reactants in the reaction are. To the right of the arrow is where the products of the reaction are. So there's a idea in science that there's conservation of mass. This applies to chemical reactions. So mass is going to be conserved in chemical reactions. Now we know there's a particular mass associated with each atom. So a simpler way for us to evaluate whether mass is conserved is to make sure that atoms are conserved over the course of reaction. So this is essentially an applied counting exercise. We want to count the number of each type of atom or each element atom on each side of the equation and make sure that those are the same. Once those are the same, we would have a balanced chemical equation. Now, if you look at the reactions I've chosen here as examples, I've basically put a kind of a blank space before each symbol. So there's a blank here before carbon. The blank is where we're going to put what's called a coefficient. So if there's no number preceding a formula, that means there's one. So the ones are kind of understood the same way they are if they're subscripted within a formula. However, we can put another number in front of a compound or molecule that is in a balanced equation if it leads us to the point where the number of atoms on either side are balanced. So we have the same number of, say, carbon atoms on each side of the equation. So you really just need to practice this a little bit. It's really kind of a trial and error, back and forth, interactive sort of thing. So we'll go through a couple here, and that should give you a pretty good idea of how to do it, and then you'll need to practice a little bit on your own. So if I look at the first reaction here, I start off with carbon, and remember the parenthetical expression here indicates phase. So this is carbon, it's a solid. And since there's no subscript, I know there's one carbon atom here on the reactant side. If I look over on the product side, again, just looking at carbon, there's also one carbon atom over here on the product side. Now, in this case, it's carbon dioxide, which is a gas, but there's still only one carbon atom. So I would describe that as carbon being balanced here in this particular reaction. And that's good. I can move on to any other element that's present in the reaction. If I look back on the reactant side, I have oxygen molecules here, O2. That's also a gas. But because this is a molecule, there are two oxygen atoms in that molecule. And that means I should also have two oxygen atoms on the product side if the equation is balanced. Now, I do. There are two oxygen atoms in carbon dioxide. So this equation is actually balanced exactly as it is. We wouldn't need to change anything. Now, leaving something blank, that can be confusing, particularly on a test. So it is perfectly okay, particularly while you're learning, if you want to write ones in there to keep track of the fact that you already did balance that equation. So on a test, I would accept the ones. Now again, once you get a little bit of experience, you're just going to leave out the ones. That's the way you will normally see a reaction. And don't really expect too many on the test that are already balanced where you don't have to do anything to have the correct answer there for the problem. Now let's look at the second one. Things will be a little different here, at least in terms of we'll need to adapt to make sure that the equation is balanced. We start with the nitrogen molecule here on the reactant side, so 2 atoms of nitrogen. Over on the product side, again, sticking with nitrogen, there's 1 molecule of NH3, which is ammonia, so not one we've talked about knowing the name of yet. It's a neutral compound, but it's ammonia, IA at the end. 2 nitrogens on the reactant side, only 1 on the product side. I can fix that by putting a 2 there in front of NH3. 2 molecules of NH3, that would be 2 nitrogen atoms, 1 coming from each of the molecules. And with that 2 in there, that would balance nitrogen on both sides of my equation. Right? I would need to do something similar for the other components, which is hydrogen. So looking here at hydrogen, I've got the diatomic hydrogen molecule on the reactant side, so that means 2 hydrogen atoms on the left, or reactant side. Now there's 3 in each ammonia, but I already decided there would need to be at least 2 ammonias to balance the nitrogen. So 2 times 3, there are 6 hydrogen atoms on the product side. And that means I should have 6 hydrogen atoms on the reactant side. Well, I can get there by putting a 3 in front of the formula for hydrogen. Now, hopefully that rings a bell. There's a similar process we might go through in figuring out the formula for an ionic compound. Right? We're looking at the different charges. We're trying to ratio those charges to find the correct formula where there's no net charge on the ionic compound. So if we're mixing a +2 with a -3, we need 3 of the +2s, 2 of the -3s, or a total of 6 transferred electrons. We're kind of doing the same thing here. 6 hydrogens on this side, 6 hydrogens on this side, but it's 2 times 3 versus 3 times 2. Okay, so a lot of similarities in some of the things that we're going to do, and helpful to recognize those similarities. It'll help you kind of incorporate this information a little more quickly. Okay, let's look at a couple more. So calcium oxide, solid here, reacting with water. And that's producing calcium hydroxide here as my product. Now, this example is here because notice there's oxygen in every component, and that's something you've got to be aware of. Particularly commonly occurring elements like oxygen and hydrogen will sometimes be present in multiple molecules in a compound, so we've got to be careful to count it everywhere it is. But unless you see reason to do otherwise, I think it's best to kind of take these in order. It's a little easier to keep track of what you're doing. 1 calcium here, 1 calcium here, that's good. Right, there's 1 oxygen here in the calcium oxide. There's also another oxygen here in the water. And there's 2 oxygens over here in the calcium hydroxide product. So remember, this 2 outside of parentheses is referring to the polyatomic ion inside the parentheses. So if I have 2 hydroxide ions, I have 2 oxygen atoms. So calcium is balanced, oxygen is balanced, 2 hydrogens back here in the water molecule, right? And just like with the oxygen, there's 1 hydrogen per hydroxide, but 2 hydroxides. So there are also 2 hydrogens on the product side. So this is another example that is already balanced. So again, you can kind of write the 1s in there. If you're a little more comfortable writing in the 1s, then leaving it blank, at least until you get used to this. Okay, I think we can fit 1 more into this video. Starting off here, KClO3, so ClO3 is chlorate, this is potassium chlorate. There's 1 potassium. Over on the product side, the only potassium containing compound is potassium chloride. So 1 potassium, that's good. There's 1 chlorine in potassium chlorate, 1 chlorine in potassium chloride. Also still good, right? We get a little complexity when we get to the oxygen. 3 oxygens here in the chlorate, 2 oxygens over here in the diatomic oxygen molecule. Well, 2 to 3, we've seen that before. We can balance the oxygen by putting a 2 here in front of potassium chlorate and a 3 here in front of oxygen, and that would balance out the oxygen atoms. We've got 6 on each side. Now, we'd have to keep in mind that we just changed something with regard to the potassium and the chlorides. So we added a 2 back here. So now there are 2 potassiums on the reactant side. So we've got to factor that in here. 2 potassiums, 2 chlorines. I need a 2 there in front of potassium chloride. Now that balances that equation. So keep that in mind. Sometimes there's a back and forth, maybe trial and error that you need to do to make sure you get all of the pieces in place. Okay, we're going to stop right there, and we'll do those last couple in the next video.